Okay, so what we're going to look at here is so I showed you my example slideshow, and that was for my mythical trinosy trait. And what I'm going to do now is show you how I could use a Punnett square to determine the genotype of one of the individuals that was on my pedigree chart that I showed you all earlier. So this is just a part of it, and we didn't look at it in detail, so I don't expect you to remember this, but this is showing two individuals. Trinosy is a recessive trait, and so that means that the shapes that are colored in on this pedigree chart indicate that they have trinosy. Shapes that are not colored in do not have trinosy. So this individual has trinosy, this and this individual have trinosy, but these three individuals do not, all right? This is a couple, they had these 4 kids. Since this individual has trinosy, I know that she has to be homozygous recessive. The genotype of this individual is homozygous recessive because she shows the recessive phenotype. The only way that can happen is if she has 2 recessive alleles. This individual right here, though, I don't know. That individual might have 2 dominant alleles. If that were the case, he would not have trinosy. He might also be heterozygous, in which case he also would not have trinosy. So that means we don't know for sure what his genotype is. Okay? We know that he doesn't have trinosy, which means he shows the dominant phenotype, but the dominant phenotype, we will see that with 2 different genotypes. Homozygous dominant, 2 dominant alleles, or heterozygous, 1 dominant and 1 recessive allele. So what I'm gonna do is I'm gonna make 2 Punnett squares. I'm gonna make one showing what would happen if this individual were homozygous dominant, had 2 dominant alleles. Okay, so the first Punnett square is going to look like this. I have, I'm going to put my unknown individual across the top, the columns. My known individual will be along the side, so my known individual is homozygous recessive. My unknown individual, if that individual were homozygous dominant, then either type of gamete would have the same allele, and that means that the resulting offspring, no matter which combination of gametes they got from these 2 parents, the resulting offspring would all be heterozygous. Okay, so all offspring here are heterozygous, and that means they do not have trinosy. They can't, because they have at least 1 dominant allele, all right? And then we'll take a look at what would happen if this individual was homozygous recessive. So again, I'll make a Punnett square, and my known individual will label the rows. So this individual is homozygous recessive. Her gametes, no matter what, are gonna have the recessive allele. This individual, though, is now, we're saying, what if this individual is heterozygous? So if this individual is heterozygous, then half the gametes that he makes will have the dominant allele, the other half will have the recessive allele. And as a result, half of the offspring would be expected to be heterozygous. And what this means is not that 1 out of every 2 kids that are born will be heterozygous. What it means is, on average, there's a 50% chance that any given child will be heterozygous and will not have trinosy. And half the time, they will be homozygous recessive. And that means that they will have trinosy. Okay? So now that we've done the Punnett squares, we can go to the offspring and we can look to see if either one of these, which one of these is most likely, and if one of these is not realistic. In this case, we can rule out this genotype for that individual. This genotype is impossible for this person to have because some of the offspring have trinosy. If this individual were homozygous dominant, none of the offspring could possibly have trinosy. So we know it's not this option, it has to be this option. This individual needs to be heterozygous in order for the offspring to even have the potential to be born with trinosy. Now you could do this with different genotypes. You could do this with trying to find the unknown genotype of one of the children, one of the offspring. So I could do that, and I'm not going to right now, but I could do that with this individual right here. If I want to know the unknown genotype of this individual, I can do the same thing. But instead of looking at this individual's kids, I'm going to look at her parents. And I could figure out, this individual doesn't have trinosy, can make a Punnett square that shows, well, she's got to have at least one dominant allele, right? Here's the Punnett square that would show it. Well, what are the possible allele combinations that she has that would give her one dominant allele? She can only be heterozygous. So we know that this individual has to be heterozygous. Why? She doesn't have trinosy, and she has these two parents. The only way that these two parents could have a child with no trinosy is if she got one of the mom's recessive alleles, but got the dad's dominant allele. So that kind of reasoning, we can explore parents, we can explore offspring. There are some times when we can't figure it out. If these two individuals had happened to have children that were all born without trinosy, so if this square had been clear and this circle had been clear, then we would know that none of their offspring were homozygous recessive. But we wouldn't know if this parent had a recessive allele and it was just by chance that their offspring didn't get it. In human genetics, most people don't have enough kids to rule that out. So sometimes we end up with somebody who's an unknown genotype just because if you only have 2 or 3 kids, there's a chance that they just won't get a recessive allele from one of the parents. With non-humans, a lot of times the organisms have lots and lots of offspring. So certain animals like fish, they lay thousands and thousands of eggs, so we can look at all the offspring and use statistics to say, okay, well, if none of the offspring are homozygous recessive, then the parent was probably homozygous dominant. And that's what Mendel did with his pea plants as well. He didn't just take 2 pea plants and cross them a few times. He crossed them thousands of times and investigated thousands of seeds. So he grew these plants and he was able to look at the offspring and say, okay, these 2 particular individuals breed, none of their children show the recessive condition. Therefore, these 2 individuals, at least one of them must be homozygous dominant. So we can use statistics to do that. That's not going to work so well with human populations because we don't have enough kids to have that sort of statistical certainty about the potential for having a recessive allele. Okay. So this is the kind of explanation that I'm going to be looking for you to do, and I'll explain in just a second how you can do that. We have a few different ways that you could put this together.